Look at this sum. 1 plus a fourth plus a ninth plus a 16th, going on forever.
Just adding the reciprocals of perfect squares.
For 90 years, the brightest mathematicians in Europe couldn't find the exact answer to this.
It's called the Basel Problem. And then Leonhard Euler came along and proved it equals pi squared over 6. Think about how weird that is. We're just adding fractions of squares.
There are no circles here, so why on earth does pi show up?
Here's how Euler treated the sine function like a polynomial to solve it. Euler didn't start with squares. He started with the sine wave.
You can write sine of x as an infinite polynomial using its Maclaurin series.
It's x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, and so on. If we divide the entire equation by x, we get sine of x over x equals 1 minus x squared over 3 factorial plus x to the 4th over 5 factorial.
And the pattern continues.
Let's call this equation 1.
It evaluates to 1 when x approaches 0.
Now, Euler applied a novel algebraic step.
He asked, what are the roots of this function? When does it equal 0?
Sine of x equals 0 exactly at pi, negative pi, 2 pi, negative 2 pi, and so on.
If you have a normal polynomial, you can build it just by multiplying its roots.
For a root r, you multiply by 1 minus x over r.
Euler assumed you can do exactly the same thing for an infinite polynomial.
He just wrote sine x over x as an infinite product of its roots. To simplify this expression, we group the positive and negative roots together.
We have 1 minus x over pi and 1 plus x over pi. That is just a difference of squares. It turns into 1 minus x squared over pi squared.
The 2 pi roots turn into 1 minus x squared over 4 pi squared.
The 3 pi roots give a 9 pi squared denominator, and so on.
Let's call this infinite product equation 2. Now we have 2 completely different ways to write the exact same function.
Equation 1 is an infinite sum. Equation 2 is an infinite product.
Since equation 1 and equation 2 are the same function, their coefficients have to match perfectly.
Look at the x squared term in equation 1.
It's simply negative 1 over 3 factorial.
3 times 2 is 6, so the coefficient is negative 1/6.
Now look at equation 2. If we actually multiplied this infinite product, how would we make an x squared?
We would have to take one of these negative x squared terms from one set of parentheses
and multiply it by the ones from all the other parentheses.
If we do that for every single term and add them up, our total x squared coefficient is negative 1 over pi squared, minus 1 over 4 pi squared, minus 1 over 9 pi squared. We can factor out negative 1 over pi squared. And look what remains. It is our original infinite sum, 1 plus a fourth plus a ninth.
We just set the 2 coefficients equal to each other. Negative 1/6 equals negative 1 over pi squared times our sum. Multiply both sides by negative pi squared, and we get the answer.
The sum of the reciprocals of the squares is exactly pi squared over 6. This is why pi is there, because the roots of the sine function are separated by pi.
Euler just assumed you could factor an infinite series like a simple polynomial. It was an unproven assumption at the time, but his mathematical intuition was completely correct. If you enjoyed this proof, like the video and subscribe to Matilda Academy for more. I'll see you in the next one.